So we've got a 6-mark question here. It's about bonding. Bonding makes very common 6-mark questions. They often give you different substances. You have to identify the type of bonding and then explain whether that type of substance, that type of bonding has a high melting point or a low melting point, or whether it conducts electricity or it's a poor conductor. This is no exception. We've got 4 different types of carbon here. Diamond, graphite, graphene and fullerenes. First thing we've got to do, identify the type of bonding. Now I've put this in a table here. A 6-marker exam, it wouldn't be in a table, and that makes it more difficult, but it is essentially. You can table them up and just answer them as individual questions one at a time. So diamond, type of bonding, giant covalent. As is graphite, giant covalent. Graphene, very similar to graphite, just one layer. So it is giant covalent. And the exception, the fullerene. Fullerene is a C60 molecule. That's a smaller molecule. These contain a lump of diamond will contain billions of carbon atoms all bonded to one another. A fullerene is a very, very simple molecule in comparison. So that is simple molecular. So it's covalent as well, but it's simple. It's a simple molecule. Simple molecular. Okay, so the melting points. With all the giant covalent, the answer is the same. They are high melting points with giant covalents. Why? To melt, covalent bonds have to be broken. So carbon in diamond, each carbon is held in place by 4 strong covalent bonds. This requires lots of energy, hence very high melting points. As I said, in diamond, 4 bonds for every carbon. It's exactly the same answer for graphite and graphene. The only difference is here there are 3 bonds around every carbon. 3 bonds. What that means is in graphite and graphene, so because of those 3 bonds, there's 1 spare electron left on the outer shell of every carbon in graphite and graphene. And that spare electron we call delocalized. Delocalized electrons are free to move. And that's the same in both graphite and graphene because they both have 3 bonds. Each carbon forms 3 bonds in both. And when we have delocalized electrons that are free to move, they are good conductors. So good conductors for graphite, good conductor for graphene. Diamond, on the other hand, because every carbon is forming 4 bonds, it's a poor conductor. Why is it a poor conductor? There's no delocalized electrons because every electron is used in bonding. And there's no ions that are free to move either. Right, down to fullerenes. This is a simple molecule. Because it's a simple molecule, it has a low boiling point. Why does it have a low boiling point? Well, the covalent bonds within the molecule are strong, yes, but there's nothing holding, only weak forces. There's only weak forces of attraction between molecules. And they require a little energy to separate. So we're not saying weak bonds, we're saying weak forces of attraction, and only a little energy is needed to separate those molecules. Right, so fullerenes and their electrical conductivity. fullerenes and their electrical conductivity. Cats. Right, after the cat interruption, fullerenes and their electrical conductivity. Each carbon forms 3 bonds. So within the molecule, they're good conductors. Why? Because of that delocalized electron. Carbon wants to form 4 bonds, but here within the molecule it's only forming 3 bonds. So they're good conductors within the molecule because of the delocalized electrons. However, between molecules, they're poor conductors. So there's nothing to carry the charge between the molecules. The electrons can go over the surface of the molecule. We've got this kind of like football-shaped molecule that the electrons can go over the surface of, but they can't go between molecules. Poor conductors between molecules. Sometimes these things are described as semiconductors. And there's a 6-mark answer.